we started with boxes that were suitable, which meant that we have decay 1 over L to the theta. And now we got the boxes that were regular with estimating the probabilities, and my decay of the order it's the minus xy. So now we can go to the third step, or the third multiscale analysis, which by and large is a souped up version of the first. There are 4 multiscale analyses, but the first and the third and the second and the fourth are similar. The first and the second, the Lk plus 1 is YLk, so you have to grow very slowly. The others 2, you grow exponentially. So, and the theorem then is that, let me take zeta 1 and zeta 0 to be less than 1. And suppose for some energy E and L0, and also some P0, we know that this boxes is S0E sub, I will go back, it's sub-exponentially suitable. And remember what it means, sub-exponentially suitable. It means that if I get the Green's function from x to y, and x and y are far apart, then I get decay, but the decay is sub-exponential, and I said zeta 0, so this is zeta 0. Okay? And notice that we got from the previous one, we have a sequence Lk going to infinity. This doesn't move. It does move, but in the wrong direction. Let me do it here. What we proved in the next one is that, and now it doesn't really matter what was the detail, we constructed a scale. So from the initial hypothesis, which is suitable, we actually proved for this scale the probability for all x. This was for some m regular, let me not write the details, was bigger than 1 over Lk to the p, right? Now, regular meant that when I came here, I had e to the minus mx minus y, right? But that means that if I want, I can get rid of these by putting an L to 100, right? And clearly, for L large, this is true, right? At some point on, this is going to be true. I don't. So what we prove is that the real k is going to infinity, such that this is zeta 0 as sub-exponentially suitable is bounded by that. So I can certainly satisfy this hypothesis with the results of the second multiscale analysis. In other words, the hypothesis of the initial theorem do imply that this hypothesis is satisfied at the appropriate L0. So we got there. We got there. Then for Lk I construct those scales. Y is going to have to be bigger than some y tilde, which depends on the parameters, which I'm not going to specify, but it comes from the proof. In the first scale, we got 1 over square root of 2, 2000 to the d. We can calculate a huge number. That's what it is. You can actually write down what you want here. We conclude, then if this is true, then if L0 is large enough as before, as usual, right? So I have to take, so I take the ones from there that can, I conclude that this propagates is eta 0 is suitable and here comes, we don't just propagate that is suitable. In this type of multiscale analysis, we improve the probabilities and we get it to the minus Lk zeta 1 for all k. I'll also mention that that's a form in which we proved it, but this theorem actually holds like the first. Forget the p. There exists now, this is a different p0 tilde, which actually depends on the y I chose bigger than that. And as before, all I need to know is that if for something really big scale, I can get this with a probability bigger than this fixed, which of course we get much better from what I got before, but this result doesn't require it. It's just like the first multiscale analysis. Only you know that if the probability gets above a certain fixed number at some big enough scale, you can do everything. It's the same type. The other two, you need to start with the right probability, but not here. Here, the initial probability does not actually need to depend on L0. And I'll just make some kind of proof with the modifications. This gets slightly more complicated, but it's basically very similar to the first multiscale analysis. So this is similar to first MSA. But let me tell you what are the differences. The difference is on Wagner. How I use Wagner. That's one. When I use Wagner, I have zeta 1. Oh, notice this is zeta 1 and this is zeta 0, and zeta 1 is slightly worse. But it doesn't matter. It just has to be slightly worse. Turns out I take some phi in between, and the Wagner how you use it has to be also sub-exponential. Okay? If I'm going to get probabilities of this type, I do need this to be less than this when I use. So phi has to be bigger than zeta 1. I think I also need it smaller than this, but so I will use Wagner with, and let me just notice that the probability that this is e to the L to the, oh, I'm using phi. I have xi on my notes, but I cannot differentiate between my xi and my zeta. So it's not going to work. Not on the board. Okay? In print is fine. We need more Greek letters, by the way. Somebody should generate Greek letters for mathematics. Okay. So this is, well, it's usual thing. K 2 e to the minus L to the zeta, L to the phi, I'm sorry, to the power beta times LD. For whatever L that is that I'm doing. So this is less than some K prime, or it is actually equals, if I just write the right constant, e to the minus beta, not, yeah, L to the phi, LD, and clearly I can just use e to the minus beta of 2 L to the phi. L is large. So that is going to be the Wagner estimate I'm going to use in this various scales where I'm going to need that. Okay. The other point here, and here I will need more than one bad box. How many bad boxes? The procedure is the same. We have to allow for a certain number of bad boxes, but the number of bad boxes I have to allow for has to be enough to give me the probabilities I want. And so, where is the calculation? Okay, so as before, I take this to be the L suitable covering. You don't really need this, but it makes life much simpler. We fix it once from the beginning. It has all the nice properties. And that's why I'm centering box in RD and not in ZD. Integers are not divisible. So, and it's worked very well. Okay, so I know, so PL is probability is a bound on the probability that a box of size L is not it's a bad probability. It's an upper bound, or if you want, make it equal here. Okay, so let me calculate and estimate, because I know that I have J plus 1 disjoint non-SES boxes with Z zeta 0. I'm fixing the energy in the covering. That's a calculation we have done many times. And I'm using capital L is some capital Y, which I have not specified yet, times little l. Well, I get the number of boxes in the covering, which is now bounded by 2y to the d. I get PL. PL is bounded by e to the minus L to the zeta 1. And I have to take e to the power j plus 1. And I want to make it smaller than this. In practice, I'll take half because I'll have some probability coming from using Wagner estimates that have to go somewhere. But since I'll have a bigger exponent, it is not a deal. Okay, so what does that tells me? Well, that tells me that the exponent that I have on this side, which is y zeta 1 little l of zeta 1, has to be smaller than what I get from this side. But what I get from this side is, no, it's correct, it's j plus 1 times e to the minus L zeta 1. Well, no. L zeta 1. I'm just with this point. I need to have that. But this is the same as saying that j plus 1 has to be at least y to the power zeta 1. So I will need, since y is going to be a reasonably large number, I will need lots of bad boxes for the probabilities to work. Okay? I need to allow for that many. J is the number of bad boxes that I will allow, because I'm not going to allow j plus 1 disjoint bad boxes. I will allow j disjoint bad boxes, but not j plus 1. Well, to get the probability I want, which is this one, I need to get at those many. J was enough to get j equals 1 for the first multiscale analysis. Here I need, but here's a fixed number. In the fourth, this number is going to depend on L. But in this one, it doesn't. It's going to be a fixed number. Okay, so I can take j, for example. I think the ceiling of y to the zeta 1 is probably good. Maybe the floor is big, is good enough, but I don't want to think about it, so the ceiling certainly works. It's not going to make much difference, right? Okay, so I need an integer, right? So I'll take j to be, so j is a big number. Then let's see, and in this multiscale analysis, and what we are going to do, and I'm not even going to go for that, because like in the first one, let me do the problem. We are now having these possibly disjoint bad boxes, of which I have j of them. But before that, let me see if things work when I put the Wagner. No, I have to make another discussion before, sorry. Let me do it here. My problem now is the following. If I only had one bad box, I just put a buffer and I was done. But when I have more, I can run into problems, because suppose I have these two. Well, the buffers will intersect. And what I really need as a buffer is to guarantee that any point outside the extended badness was actually in the good region, was contained in a good box where I could get decay. So I cannot do that, because I cannot just do that. So what I have to do is to somehow, okay, I have these two, let me know. I will take a box like that with a buffer around, so anything outside. This is probably, before I had what? 2 alpha plus 1 L. Maybe for those I need 4 or 5 or 6. It's a joke. I have it written, I can do it, but I don't think people want to see all the possible details of that. The problem is that now I have J of them, and I could put 2 together. I could even have a situation where all the J's are somewhat together and they'll be in a gigantic bad box, which will be some constant, I don't know, 10 J alpha plus 1 L. Oh, the 10 I'm not sure, I can, but there is a number like that that you can calculate that tell you how big the thing. But the point is that I have 1 to J bad boxes, so I can get agglomerate. When I put them so that I could have 1, I could have 2, I could have up to J, right? That I get together. So I will have boxes of size 2 Ki alpha plus 1 L. I have to calculate the Ki correctly, where I goes from 1 to J, and basically I'll have that this will contain basically I bad boxes. I'm not going to have J of them, but I could have J only if all the boxes are separate. But I have to worry that all of those boxes will have the Wagner estimate I need. But I only have J possibilities, okay? And all of them, the size in the end is less than capital L. I don't have to use free little l. Capital L for the polynomial side will work fine. Not polynomial, for the other one, I think it works fine. So when I do the Wagner estimate, or when I do the deterministic thing, let me put it here. Is that 1, I still haven't told it what y has to be. That comes when you do actually the calculation for the Green's function. Is that to tell you what it is. But I know that J is this number, and I'm saying I have no J plus 1 disjoint bad boxes, right? These we already took care by this choice of J. The probabilities are good. But I am going to have Wagner for the full box. And remember, Wagner is now L to the phi. And so when I calculate the probabilities, let me okay, these I'm not going to repeat this calculation. This is not going to repeat this calculation, but what I'm going to get is that P of L okay. let me actually write the whole thing I had before. The first one, because this you end up having to work with this. It was 2y to the d e to the minus L zeta to the power zeta 1, and actually okay, and here I should put j plus 1, so I just put y to the zeta plus 1. I am going to get contribution from that, which is calculated here, e to the minus beta over 2 L to the phi. And now I have sizes of boxes, let's say L1, L2, L capital J. These are the sizes of boxes I need to put inside, and to put inside all the bad boxes, but at the same time that I put inside all the bad boxes, they are far apart, so if I go outside, and they are all, of course, less than equals to L, they'll be actually less than some constant times little L, which is fixed, and for all of those lambda I of A, for all of these things, I want to get this to be, well, for every A which is the center of a box in the covering. So what will those give to me? Now each one of them is going to give e to the minus beta over 2. These are also all bigger than L, so I just use, that makes it bigger, so I can use. And how many of them I have? Well, turns out, at least for my notes, that I get j squared times the number of boxes. I get something like that, and this, of course, is basically y over 2 zeta 1. I'm not sure about the 2 right now, but it doesn't matter. The point is that when I do that, I get from here that this is equals then, well, what did I put? Okay. Then 2y to the d. This is PL, right? Let me write like that. PL to the power, and we put j again, plus 1/2 somehow I consolidate, okay. Beta oh, sorry. Now this is phi. Sorry. This is phi. Okay? The fact that phi is important because phi is bigger than zeta 1. And that allows me to bound all of those by this. I'm simply using the fact that if I want to put here, just put this is capital L divided by y, which is a constant, to the power phi. All of these things, if you put everything together, and since this exponent is smaller for them, you have this bound. Now, you look at this, it's very similar to you have for the first multiscale analysis, right? Except that before here, we had 1 over L to the P. You do the same sort of procedure. And doing the same sort of procedure, you find out that you are going to need y to be basically, I'll just write what it is. It just comes from the calculation. It's some constant. I think I had 11 in some, but I'm not sure the 11 is correct. So 1 minus zeta 0. That turns out to be what I need. And you find that PL end up being smaller than this for, that's the probability I want. No, zeta 1, sorry, for some large L. So you get the probabilities, okay? And what I want to go to the next multiscale analysis, not leave it for tomorrow, but let me just say the deterministic is what I have here, and basically I do the same game as before. I have bad boxes, which are the extended bad boxes, where they include all the bad, and everything outside is good. When I go from one point to another, I can actually count those. I have to show that, as before, that those things don't matter, because, and I only don't gain the decay from them. So I always want the distance from here to here that I'll go will be the distance minus the length of all those things that I can estimate, and it's some constant j times L times some constant. And in the end, you get what you want. This is very similar to the first one. It's just more complicated because you have even more, but the ideas are the same. And the way you solve these and show you get the probabilities are the same. So from here now, we go to the force. And let me start with the single energy. So maybe it will be actually, and our starting point is that we had scales, what you just construct, such that the probability of lambda Lk is zeta 0 E SES is bigger than 1 minus E to the minus Lk to zeta 1. That's what we're doing before. And this implies that same thing, that the probability that is Lk to the zeta 0 minus 1, this is a negative number, regular, is this. This will be true. No, this is always true. I'm just translating this into this. So these are going to be the hypothesis of the next multiscale analysis. And basically the ideas will be similar. Okay, I have this. And let me actually put an extra one. Actually, I don't need this. Let me just, because I'm going to, no, I do. So I'm going to have this. Zeta 2, zeta 1, and zeta 0. And I know that the probability that for all x is m0, and m0 here is exactly L01 minus zeta 0e regular. This is e to the minus zeta 1, L0 to the zeta 1. So I take gamma, and there will be a few more conditions, but basically the condition I need is that it's smaller than zeta 0 minus zeta 1. I define Lk to the gamma, and then L0 large enough. This reproduces itself. The probability for every x, this is, well, I'm going to lose something. Let's say 2. I'll put 4 here. You lose something. Irregular is bigger than 1 minus, but here I put a zeta 2. I lose a little bit. But I can do it for all of them. The deterministic part is always the same. You just have the boxes, you have good boxes, you have the bad boxes, you deal in the same way. Let me try to tell you what is different. And what is different here is going to be the number of bad boxes. So let me look at the probabilistic estimate. That's where I want to start. Okay, so for the deterministic part, I will require at most, I don't know what J is, but I have disjoint bad boxes. Then I have the Wagner. For the whole box, I still use L to the phi, and phi has to be bigger than zeta 1. And all boxes, those as before, lambda Li, all extended boxes have the Wagner with e to the Li to the phi. And then I calculate the probability as before. Now this is 2 L gamma minus 1 to the d. This is just the number of points, PL, j plus 1. The probability of the second one was this, phi of this is phi. And the second one, and I seem to have a j, it should be the same, it's a j or j square. But here is the number of points. This is the same one as we did for the previous one because the Wagner we're using is exactly the same. So we have that. And this thing here, our bound is e to the minus L of zeta 1. Now, if I do that, and what do I want? I want this to be e to the minus L to the gamma to the zeta 1 power. This is e to the minus L zeta 1, right? I want to propagate those things. I'm not quite sure I'm losing the probability. I need zeta 2 in this one. Okay. So, what do I see I need here? That is clear. Well, it is clear from here. If you look into that one, this term doesn't matter, but I will need that L gamma zeta 1 has to be bigger than J plus 1 L zeta 1, right? Otherwise, this term cannot be smaller than this. But this tells me that J plus 1 now is going to be bigger than L gamma minus 1 zeta 1. The number of bad boxes now is going to grow with the scale. But of course, this is much smaller than capital L because this is gamma minus 1. It's not gamma. So, we take J depending on L. And I'm going to put the floor here, doesn't matter, because I'm actually not going to put zeta 1 here. I'm going to put zeta 1 prime, where zeta 1 prime is chosen to be slightly bigger. I need to give me a little bit more room, okay? Under this condition, at least this first part gives that. The other part, because the phi is bigger than everything, gives you the estimate. So the probabilistic thing estimate as long as you go that. Oh no, I should say that if I do the Wagner part, I should not just ignore it because it actually tells you something here. I can do it here. The Wagner part here look at the last term. And the last term is I should have JL to L gamma minus 1D e to the minus beta to 2L over phi. These also I want to be smaller than, I'll put a 1/2 here, but it doesn't matter, 1/10, doesn't matter, L gamma zeta 1. But this implies, if you go through that and now replace it, but what we found we have to use, So this is L gamma minus 1 zeta 1 prime. This actually stipulated doesn't matter. It tells me that gamma zeta 1 has to be less than phi. So actually, the gamma I need to take is actually smaller than phi over zeta 1. So I don't think I put it here. No. Did I write it here? Okay, so I actually have to I fix a phi bigger than zeta 1, and I also require gamma to be smaller than phi over zeta 0. This can all be done, and with that, actually, the probabilistic estimate works. The deterministic part works like before. You have the bad box, you have the good boxes, you do like you did in the second multiscale analysis, except that you have to take care of so many boxes. But it's the same idea. I mean, the calculation is the same. So this gives you the force, but I want actually not the force, but I want the energy interval multiscale analysis. And I could go straight from the third to the fourth. But since I already described the single one, I'll go from the single one to the energy interval. It simplifies a few things. So that is the fourth, or maybe now it's 4.5. But this is the energy interval. MSA. And I will actually, I don't think I have zeta 2 here unless I make a mistake, and I seem to have got zeta 1, so I don't know what, but maybe I have to go and look back and see why I wrote it like that. It doesn't matter, but so let me hypothesis, and my hypothesis now is that I showed is that we can find sequence going to, or actually let's put it that way, I know that there exists some M0, which now it will be fixed. I mean, and there exists L0 and an energy such that the infimum in X of the probability that lambda L0 of X is M0 irregular is actually 1 minus e to the minus L to the zeta. So now here I'm going to lose something. So let me call this one, let me call this one zeta 1. Okay. Okay. How do I state it? Okay. Then there is some mass depending on, and now I am going to have here zeta 2, which is smaller than this, because I'm going to lose something. So there is something I'm fixing the m, so there exists some m tilde positive, there exists some delta positive, and there exists gamma that satisfies, well, all sorts of things as before, such that if I write e minus delta, and now I look at the interval e plus delta, then for every x and y which are separated, the probability that for every energy in I, either lambda 1 or Lk, or lambda Lk of y is m0 over 2 e prime regular, oops, this is 1 minus e to the minus Lk to the zeta 2. So that is a statement that you have every energy in the interval, the price you pay, that you have to use the two disjoint box things. It either happens for one or happens to the other, but then the probability is good. And this uses some new ideas. And one of them I will actually the key idea here that one has to use is the Wagner probability between disjoint regions. So let me prove that today, and then I will use it tomorrow to try to finish this, and then I'll show how you extract localizations from the multiscale analysis. The idea that one is going to use is the so-called Wagner estimate for disjoint regions. And so let me take two subsets of CD, but they are disjoint. I can put finite, otherwise the estimate is infinite. It's still true, but it will have the number of points in the estimate. Then, for every epsilon, the probability that the distance between the spectrum of H in theta 1 and the spectrum of H in theta 2, the probability that that distance is less than or equals to epsilon is bounded by K mu, which is what you get for Wagner, but you get the product of the two volumes. They're not necessarily the same. Wagner, you get this. This you get the product of the two Wagners. And at least in this case, this is very easy to prove. And so let me call to a given subset theta omega theta to be the collection of random variables associated with theta. And let me use p theta and expectation of theta to denote the probability and the expectation associated with these random variables. Now, the point is that if theta 1 and theta 2 are independent, disjoint. These are independent random variables, right? Independent collections of random variables. So, the first thing is that I look at the probability that the distance of sigma lambda 1, sigma lambda theta 2 is less than epsilon. The first thing is that the only random variables here is the random variables associated to the same thing, to the union of these two regions, right? There's nothing else there. Well, but then, since they are independent, I can first, I take the probability with the random variables in theta 1 that the distance between the two spectra is less than epsilon, conditioned. And since they are independent, I really fix the values of the random variable theta 2. And then I just have to finish by taking the expectation of the remaining random variables. And the point is going to be that these you can estimate uniformly on those, because let me take the spectrum of this. It has random variables that depend on those variables of but they do not depend on the random variables in theta 1. And since they do not depend on the variables of theta 1, I simply notice that the probability in theta with respect to theta 1 that the distance of sigma h theta 1, sigma h theta 2 once is less than epsilon, once I fix this variable, is less than equal. I can order them, let's say, I use the minimax principle to get those. So they are ordered and also. This is less than the sum, where j goes from 1 to theta 2. The probability that the distance from lambda j of omega to the spectrum of this is less than epsilon. But these I can estimate by Wagner, and actually I should probably still say here, given this, but this I can estimate by Wagner independent of that, and this gives me K mu of 2 epsilon. Did I have the 2 epsilons the way I wrote it? Yeah. Times theta 1. But how many of those do I have? Theta 2. Well, this is independent, so we are done. And where did I? And we have that estimate. It's 4 o'clock, so probably I have to stop. So tomorrow we can use that to finish quickly. I'm not going to all details. The fourth multiscale analysis, I want to get the consequences of the multiscale analysis, because you don't do it for doing it, right? It's not just for the exercise. It tells you things about the system. It gives you many things. And it's much easier to derive the consequences than to do the multiscale analysis. In most cases, not on Bernoulli. Okay, I'll stop here.